So we have a proton that's accelerated through a potential difference V before passing into a region of uniform magnetic field into the plane of the screen as shown here. Find the voltage necessary to give the proton a speed little v as it enters the magnetic field region in terms of its mass, its velocity, and its charge q. Well, let's see. In order to start this, the energy that it has is the work that we do on it, which is going to be the charge times the potential difference. So work, which is QV, is going to be manifested. It's going to be its kinetic energy as it goes into the mass spectrometer. So that's 1/2 mv squared. Capital V, little v. Voltage, speed. Got to be careful of these two. Which implies then, solving for the voltage, the potential difference, that's going to be m times velocity squared over 2q. Okay, that part wasn't too bad. Let's take it a little bit further and determine an expression for the radius of the proton's motion in the uniform magnetic field region. All right, well, the force, the magnetic force on it is QVB, and that has to equal mv squared over r because it's moving in a circular path, which implies that r is going to be equal to mv squared over qvb, which is equal to mv over qb when we cancel out one of those velocity factors. Radius in the uniform magnetic field, mv over qb. All right, taking another step, sketch the path of the proton in the magnetic field. Well, let's see. It's a positively charged particle, so this looks like a right-hand rule problem. Point our fingers in the direction that it's moving to the right of the screen as it enters the magnetic field. Curl your fingers into the screen in the direction of the magnetic field, and you're going to see that initially you have a force up. But as that moves, that's going to turn it. You're going to get this curving path, so it travels something like that. I'm going to see a circular path in that direction. All right, last one. An electric field is applied in the same region as the uniform magnetic field, so over here. Determine the magnitude and direction of electric field required so that a proton passes through the region in a straight line. So now we're setting this up so that we have a velocity selector, so that the particle goes through unhindered. Well, the first thing is we saw the magnetic field, the magnetic force was pointed toward the top of our screen. That means that our electric force is going to have to be down. Therefore, our electric field is going to have to point down because it's a positive particle. And in the velocity selector, we have the electric force equal to the magnetic force, which implies that QE equals QVB, which implies that the electric field strength has to be equal to V times B. All right, hopefully that gets you a good start on moving charges in magnetic fields. Thank you for watching educator.com. Make it a great day, everyone.